Hey y'all. Today, I'm going to take you through a really cool use case, functional use case that my colleague Tamara built on how to run an integrated ELT and ML pipeline on Stripe data within Airflow. So if you want to follow along with me for this video, head on to the Astronomer Learn page, and you can see all the steps that I'm going to go through here to create a ELT pipeline to transform some data that is modeled after the Stripe API. And then what we're going to do is we're going to, based on the different customer satisfaction scores and product type, we're going to try to predict the total amount spent per customer, hoping to figure out, hey, what areas of customer satisfaction we want to focus on. And these are going to be the end graphs that we're going to produce. So predicted versus true values on, hey, what areas are we going to actually need to work on and improve our customer satisfaction score, the predicament of every company. So without further ado, let's head over into VS Code and I'm going to start actually building this. So before we get started, I actually want to call attention to a couple things about this repo that might be different and are kind of new and are pretty useful actually for local development. So number one, we're using an Astro CLI generated Airflow runtime, so easy. And if you want to just copy this down from GitHub, you totally can. And then you just run astro dev init, astro dev start. Don't run astro dev init, and you'll be all set. Then what we're also going to do, and this is kind of a trick, if you want to mimic, interacting with S3 bucket in kind of a development environment, is that here you can use mini.io, which is a packet or requirement that we installed. And what mini.io is basically it's kind of a way to mimic an S3 database on your local machine. So here, and if you just download repo again, you don't have to set any of this up. We're going to say, hey, when we're connecting to AWS, we're actually connecting to mini.io admin. So that allows us to use a mini.io S3 bucket rather than you needing to do all the connecting to your actual AWS account. We're also doing something that you should never do in production, which is just using the local Postgres database for our data processing. So this definitely isn't best practices. You're not going to want to store large amounts of data just in your local Postgres or your backend database. But for the purposes of this is just kind of an explainer. So you don't have, if you want to connect this to any other database, you're more than welcome to, and you can just replace everything correspondingly. It's another Postgres database just to update the connection details, and it'll automatically take effect. But I just want to kind of show you these because they are pretty useful tools for when you want to test things locally without doing a bunch of external setup. And then finally, within the Docker Compose override, this is how we are actually creating the mini.io service. So here it's just provisioning mini.io, using a service, and just kind of all the details there on our local Docker instance. So we're using Docker to run Airflow because we're using the Astro CLI, best place to run Airflow locally. So the first DAG that we're going to write is actually one that we're just going to use to kind of mimic pulling the data from an external service. We're not actually going to be connecting to Stripe because this is just kind of a demo. Instead, we're just going to run a script that's included in create mock data. So there's this include directory where we have mini.io, plots, Postgres, all the extra information we need. And then you can see here we have some mock Stripe charge data. No, I don't need help with CSV files. Now, in our finance data ingestion script, what we're going to need to do is actually take that information, populate it into our mini.io database, because when it's spun up on your first creation of this environment, it's not going to have any data contained with them because it's a fresh mini.io environment. So first thing we'll need to do before we actually do anything fun is import all of our packages. So here, decorators, pendulum, date time for good date time, the local to S3 operators, so you can bring files from our local system into that mini.io instance, our S3 create bucket operators. So you'll notice here when you're interacting with mini.io, you'll just use AWS operators and use mini.io's S3 instance as credentials. Then import OS so we can read system messages. And then we're going to include generate mock data so we can call that mock data script. Then after that, we'll use our AWS connection ID and data bucket name here, just what we've already defined for our previously in that AWS connection string that uses mini.io. And then we have our data bucket name, which is just, so make sure it's consistent across all uses within this DAG. Then after that, we'll initialize our DAG in finance data, and we will create our first task. So in this task, it's going to be real simple, which is just a Python decorated task that's going to call that Python script that's in that include directory. And then we will create a bucket within our local mini.io S3 bucket. So again, using that data bucket name. And then what we'll do is actually use a dynamic task where we're going to upload all those different Stripe data files in parallel. So this is kind of mimicking how you'd want to do this in production, because you're never going to want to load like tons of different files on Stripe transaction data sequentially. That'll just jack up your processing time super high. So always recommend use dynamic tasks for anything you need to scale. Anytime you need to scale one task to encompass many different variables, or many different task instances for many different variables. So here we have a list of kwargs, and then this is just going to get every file within our mock data, set the destination key within mini.io, and where it's pulling from using that file name, and then it's just going to keep adding them into that bucket. So just constantly appending, and then it's going to return that complete list of all those file names. Then what we'll do, using those file names that they have, they have all of their source and destination paths all created. So that's within that upload kwarg. So that's what's going to be returned by there. So after we generate the mock task data, get all the credentials for there that we need, and then we're going to use that. So we don't have to have this whole formula for a bunch of different kwargs going into our local file system S3 operator. So this makes it really nice and clean when you want to run another task downstream parallel. You can just use the output as the expand field, and then boom, we have upload kwargs, and now this will create like 20 different file instances, uploading all those files in parallel. So maximum efficiency, maximum power. Then what we'll do is create bucket and upload mock data. Then we'll just declare our DAGs in finance data, and then it is time to start building our next DAG, which is going to be taking this raw data now that we have in our file system and transforming it so we can use it for ML. So now that we are going, we've got all of our raw data, now we're going to actually ELT it into usable data for ML processing. So what's happening here is we're using deferrable operators at the start of this DAG that are just going to wait for data to land in that S3 bucket. So we're just going to point it towards there, say, hey, once a new file arrives, then actually trigger and start processing. And then we're going to ELT it. So we're bringing it into our database and then transforming it there, which is sometimes a better approach for processing your data if you can do more efficient transformations within your database. So after we've gotten our description all set up, which is always super fun, we have our decorators. So here we're going to use task group, task, DAG. We're going to use an S3 key sensor async. So this is how we're going to use it. That async is basically deferrable operator. Then here we have the Astra SDK. So this is going to allow us to just execute SQL code in any database and just write these functions with a lot less boilerplate code. We also have our files, tables, so you can interact and store things as file and table objects pointing to external tables or external files, so we don't just keep calling their full name. And then we have the load file operator, just again making it easier to load files into a database, and file type, which is just a constant that we can add as a parameter to define which type each file and table are as we load them into our database and then transform them. So now that we've got all of our imports set up, what we'll do next is can set kind of all of our global variables for this DAG, our database connection ID, Postgres, just start using our local database, again setting that data bucket name, and then also setting our poke interval. So this is saying how often is the deferrable operator going to check that location for a new file. And once we've got all those set, what we can do next is not click out of this file, but use the add_AQL_transform method. So here what we're going to do is write a SQL statement. So this is just what AQL_transform is going to do is just take this SQL statement where we're selecting details about each charge from each inline charge. So the table that we're going to feed this is obviously a charge table, one of those raw data sets we got earlier. And then we're going to say only successful, only ones that were approved by network and paid. We don't want any bums in our data set for ML, because why would we want to train our ML processes on people that don't pay? So the next thing we're going to do is going to make another ACO transform. So again, another transformation, we're making an ELT process. There's going to be a lot of SQL transformations if you're doing it within a database. So here we're going to, again, read in from our successful charges. So this is going to be downstream of that previous task, and group them by customer ID. So we're going to figure out, hey, what is the average amount each customer is spending with our business? After that, we are going to join our amount of average successful amount our charges spent by customer with the average customer satisfaction. And that's going to come from our satisfaction table. So what we'll do this join on is just on customer ID. So success or satisfaction customer ID versus the amount of money they spent per customer. So that way we can correlate, hey, are our biggest spenders, are they the happiest or are they not? And so now that we've got that done, we can all of our transformation tasks, and there are a lot because this is an ELT job. We are then going to define our DAG as finance ELT. So here within our finance ELT DAG, what our first task group will be is just using our mini.io instance, waiting for that ingestion change. So we're just reading the connection, authenticating it to actually be able to look in this mini.io instance, and just looking for when that ingestion data and the satisfaction data from those raw files has been loaded. So this is going to use that ping. So every 60 seconds, it's going to ping that location, see if the files have been deposited there. If they haven't, then it's just going to sit and then wait again for another ping. And so the advantage of deferrable operators is instead of taking up a task slot on a worker, they go onto the trigger, which is kind of just a worker that takes all the deferrable and async tasks and just does all of their polling for them. So really helpful feature to have. And that's one of the later features in Airflow. So I think you need to be on 2.4 for that. Now, after we're done with that, we'll just declare ingestion done. So just declaring it as a task group there. So again, using the task API with decorators. And then after we're done with that, we've identified that those files are actually there. We're then going to have to define a task that's going to retrieve them. So here we're going to create a Python task, basically, that's just going to return the input files and output files for each, obviously, input raw data, and where they're going to be then deposited in our backend Postgres database. So here we're just going to be returning all the details for all of these files. We're not actually going to be uploading them. So similarly to how we did in the last task, we're going to collect all of these, not keywords, but input and output fields, initialize them as a task so we can use them as their output. And then what we'll do is actually create a separate task downstream using the Astra SDK's load file operator to dynamically generate tasks to upload all of these files in parallel into our backend or into our backend database. So now we've got our files brought in from S3, they're loaded in our database. Now we're going to need to actually run those transformation tasks that we created earlier. So first, let's just set our logic for how the ingestion will be done. So checking for ingestion and putting the files, and then from S3 to our backend database again. Then what we'll do is actually define our temp successful task. And what this is going to be is just selecting our successful charges and then setting the table that's being read into them as those charges that were ingested. So instead of being each unique charge file, there's like 20 different files. Now they're all in the same table, which is called in charge. So now files have been uploaded. They've been only the successful charges have been selected into a temporary table. Then we're going to take that temporary table and average it, find the average per successful customer, and then finally join that with our customer satisfaction data. So we don't need to do any average on that. We just want to know the raw amount of customer satisfaction per the amount that they're actually spending. And then the only things we have left to add to this DAG are actually declaring it and adding the AQL cleanup task. So this task will run in tandem while all these transformations happen and actually delete any temp tables that were created. So it's a nice little helper task, so you don't have to define another task logic to clean up your temp tables. When you're doing this kind of transformations, you don't want to keep the raw data after you've transformed it and loaded it. You probably, even if you had it in the database or we're using it down the road, probably go store that in data lake because it'd be much cheaper. And then we'll just declare the DAG as the finance ELT. So now got our clean data. It's ready for usage in our ML model. So let's go and finally build that ML model. So now here we have our final DAG where we're going to take our clean data and then generate those plots, run some models, do some tests, and then generate some plots that I showed you at the beginning of this DAG. So before we do that, we have a whole list of packages to import for actually being able to machine learn. I actually haven't said it like that in a while. Decorators, DAG and task per usual. Then we're going to import pendulum datetime, SQL as AQL for Astro. So giving those kind of transformations, table of metadata, someone we used them last time. Airflow configuration. So this is how we're just going to pull some configuration variables from how Airflow is actually configured. And then we're also going to have pandas. Good old pandas. If you work with data science, data analysis, you know you need pandas. And then we have sklearn, and these are scikit-learn. So these are different regression models that we'll be using within for our machine learning. Finally, we have NumPy, which again, great data science tool, and OS, so we can again read levels from our local OS. Now, after we've done all this, we'll create our second standard thing, which is just our list of all of our constants for our DAG. So here we have connection ID to our mini.io instance and to our Postgres database. So we're going to be depositing those files into our mini.io instance. Or actually, no, we'll be depositing them in our local files. So then DB schema we'll be using your data bucket name, so finance, you know what it is. And then we're just going to have an environment variable to say to use our local environment. It will become apparent what that is later on. I'm going to keep a little bit of mystery for you. So after we've done that, we are going to create one mammoth of a task. I think this doesn't set the record, actually. I've seen longer tasks, but I think a cool 60-line task. So let's break it down, just kind of go step by step. A lot of it's just transforming data, which is what you need to do if you're doing ML. Surprise, surprise. So here we're going to be doing feature engineering. And so this is finding, hey, what are the features of this data set that we want to identify, want to train our model on. And so here we're selecting our models from scikit-learn, selecting some preprocessors, so scaler and an encoder to process our data. Then we're going to create a data frame from the average amount captured. So this is going to be using that data we transformed in our previous DAG for dropping certain columns that we don't need. So when you're training a model, you typically won't want to have your sought after variables as part of the training. So then what we'll do is train the test. So we're going to create different training sets and different testing data sets. So we can generate comparison or generate models and predictions on some portions of the data and then test them on other portions of the data. So kind of segment it. Then we will do some pandas data frame, create some panda data frame using those splits, index them, define our numeric columns. So just knowing what the columns are for this model. Then again, calling the standard scaler. So we're going to fit our X training columns to this scalar. And then what we're going to do is also transform for our X test. So this is a train test split. It's scaling our numeric features, so assign them to a standardized scale. And then we're going to one hot encode the categorical feature product type. So encoding it as a product type. Then you can see we're just kind of doing that again, transforming and returning some data sets. So this is just running those encoders, running those transformations to fit them to that scale, indexing them, so dropping some columns that they don't need anymore, resetting it so that they can start testing this data, dropping the product type. And then what we have is our X training data set, our X test data set using. So now we've featured engineered, and basically what that means is just we figured out that we've measured the features are the measured inputs. So just the independent variables that we brought in. So all that information about customer spend, about customer satisfaction, and the target variable. So we're using all of those different variables to predict how much is a customer going to actually spend with us based on their amount of customer satisfaction. That's the root of this ML task. We want to figure out the important information on, hey, when someone walks in the door, if they're happy, they're going to spend $100. And then we can just focus on the happy customers or make the unhappy customers happy, but one's easier than the other. So now we're going to actually take these feature engineers, or take the engineered features and the targets. We've configured all the different details we need for our ML model. And then what we're going to do is train that model. So you can see here we have define, train model, where we're bringing that feature engineering table, the model class, the hyperparameters, all the different things we need to actually run our model. And then what we'll be doing is training that model. So here you can see we're going to read in the xtrain. All the feature engineering tables contains our xtrain data frames, our testing data frames. Read them all into this next training model task. Then indexing them, fitting them to the model, or training data sets to the model. Then what we're doing is using those predictions to try and use xtrain and xtest to actually try and predict our y values, which is how much money they're going to spend. Which is average amount captured here. So then we're going to use some R2 scoring, and R2 scoring is just saying, hey, how accurate do we expect this model to actually be? Is it going to actually predict our customers, or is this just all kind of correlation, not causation? So we're going to get that R2 score, save it, and then that'll be for each individual feature. So it'll tell us how much each individual feature contributes to that actual predicted value. And then for feature importances, we're going to read through that data frame, and we are going to create a data frame that says, hey, for each feature, each column, each data point, how important is that to the actual eventual model outcome? Then we're going to sort those values by importance. We're going to print them out, and then we're going to also show their actual raw R2 coefficient. So how important they are, and then what their corresponding R2 coefficient is. We have R2 train, R2 test, printing those out for our convenience. And then we also have our Y-train to data frame, pandas data frame, just collecting all those different values that we created, and again, returning them so we can use these data sets downstream to actually generate those nice pretty graphs that we saw at the beginning. So now that we're done setting up our model training, setting up our ingestion, we are in our feature engineering. We'll then declare our DAG. So here, just setting our schedule to be whenever our previous ELT job completed, then we're going to want to trigger this ML pipeline to consume that clean data and then use it for its ML training and predictions. So after that, what we're going to do, similarly to our last DAG, is we're going to, again, just declare that feature engineering table using that model of satisfaction we created earlier. And then what we'll do is actually set some configurations. So if it's production, so if it's production, this is just kind of, it's not actually how we're going to be working here, but if the environment was prod, this will get all the details about Kubernetes and then run them on a Kubernetes task using the Tasks API. So if you want to run these, and sometimes with ML, you want to run it on a specialized Kubernetes cluster. So this is how you can do that. But since we're going to be running it locally, we also have this else if environment equals local, and this is just a global variable that you can change based on, hey, when I'm deploying in production, switch over. So this is kind of an example of how you might want to implement that. Then, since we're doing locally, I'll kind of focus on what's going to happen here, where we're going to then just train our model task on our local machine using our local compute on a MacBook, so it should be able to handle the job. And then what we'll do is say else it's on either of these two environments, then we're going to just declare there's been an error, there's been an issue. And then finally, or not finally, the model results. So we're going to save them. So we're going to initialize that using that model task definition we created earlier. Train model task, partial, and then expand it for these three different models. So we're actually going to train our data on the random forest regressor, the rich CV linear regression, and lasso. So rich CV and lasso linear regression is just a category. So that is, instead of just one ML model, we're actually going to do three. So you get 3 for the price of fun. And then our next step, as I promised, is we're going to actually plot all of these results on some pretty MATLAB plots. And so obviously MATLAB and scikit-plot take a lot of configuration to get right. So you'll kind of see that illustrated here, where we have our giant plot math results. And so here we'll have, and sorry, I got joined by the Datadog here. We're just using that matplotlib, Seaborn, including plots, getting the Y-train, everything that, all those good data points, and then we're just plotting them on those scatter plots. So when you're done with this DAG, and you'll just kind of see all the different details here, configuration, just defining the look of the DAGs. You do a lot of that, shockingly, when you're defining DAGs purely via code. And then we're going to create them dynamically to say, hey, for all these model results, create some plots. And then once you're done, these will all appear within your plots folder. So you can see here, I actually already took the help of running it ahead of time. And you can see that I actually, let me just move my things, you run that little screen there. I have my true versus predicted values, and you can see them plotted over linear regression, lasso, you can see again linear regression here, random forest. So this is saying, hey, based on how much, or based on how happy my customers are, based on these values, then this is how much I predict that they're going to spend on the left here. So really cool functional little use case here. Really recommend you go try it out at home. It's a very cool way to kind of just get into the beginning of ML processing. And the way you'll actually want to just trigger all these DAGs is first you just trigger your helper DAG, then turn on your finance ELT and ML job, and you'll see that they are, because they're scheduled on the previous one actually completing, you'll see that here we have the finance ELT is linked in the finance ML, but then also our finance ELT DAG, because it's starting with that waiting for ingest asynchronous task, it's just going to sit there and wait on that trigger node. So that's why you don't actually need to trigger or schedule it, because it's just going to constantly ping that. And so that is all I had for you today. I hope you enjoyed. Please go try this out. Big ups, big thank you to my colleague Tamara for creating this. And have a great rest of your day. Data Guy out.